Good day. Today my presentation is drug release from a biodegradable chemo-radioembolization agent loaded with Sm-153 Radionuclide and Doxorubicin. This will be the flow of my presentation today. Starting off, is liver cancer is the sixth most common cancer and the third leading in cancer death worldwide. It's predicted that the incidence rate and the mortality rate to be increased by more than 55% by 2040. And liver cancer is the death by liver cancer is the fifth among males and seventh among females. The treatment options of liver cancer is based on the staging. So very early stage and early stage has more options of treatment such as ablation, resection, and transplant, while intermediate stages is transarterial embolization, advanced systematic therapy, and then terminal stages transplant or best supportive care. My focus will be about transarterial embolization. Now, what is embolization? It's when a procedure using particles or microspheres to block the blood supply towards the tumor, starving the tumor from all the nutrients and blood. In the case starting off, we have treatment, we have conventional TACE, which is conventional transarterial chemoembolization, where we have lipidol, the drugs, and embolizing agent injected towards the tumor, where the embolizing agent blocks the blood supply, and the lipidol and the drugs go towards the tumor so that tumor cells can uptake the chemotherapy drugs. Next is DB-TACE, which is drug-eluting bead transarterial chemoembolization. The beads are loaded with the chemotherapeutic drugs injected towards the tumor, block the blood supply, and the release of the drug out of the beads. Next is TARE, which is transarterial radioembolization, similar to TACE. However, here we have a radioactive radionuclide loaded into the microsphere, injected towards the tumor, allowing the radiation to kill the tumor cells. So transarterial administering of the microspheres using the hepatic artery and injecting the microspheres towards the tumor in the liver to block the blood supply and also release the chemotherapy drugs or allow the radiation to kill the tumor cells. The uniqueness of this treatment is due to the liver itself, which has 75% of the blood supply to liver cells comes from the portal vein, while almost all the blood supply to the hepatic artery goes to the liver tumor cells. Therefore, when we're blocking the blood supply towards the tumor, we're not affecting all of the organ. Now, currently, TARE and TACE combined to get treatment is conducted by TARE followed by TACE, which is showed that median overall survival in the combined therapy is 36.8 months compared to TARE alone. However, there's limitation where there's no combination in one formulation or delivery system. Multiple treatment courses is required, therefore it's very costly and causes psychological burden on the patients, and has a higher risk of complications due to be admitted into the hospital multiple times. Another limitation is deuterium-90 is a radioactive or the radioactive radionuclide that's being used in transarterial radioembolization, which has no imaging properties, has a half-life of 64 hours. It's only produced in Singapore, Canada, and China on the whole entire globe. Therefore, it's very costly for other countries to request the deuterium-90 because it's a radioactive material. Therefore, the transportation is very costly and the production as well. So alternatively, Sm-153 will be one of the choices. It's a theranostic radionuclide, has a half-life of 46.3 hours, and can be produced by 223 reactors in 53 countries. Therefore, it's relatively cheaper to produce. As well, there is a lot of countries are possible to make the samarium radioactive. Therefore, they don't need to buy it from somewhere else radioactive. Therefore, cut down the costs in transporting radioactive material. Now, what's a theranostic radionuclide? Similar to samarium, it's combining diagnosis and therapy. So you have the gamma and beta emitters such as samarium, where the beta energy for the treatment of the tumors and the gamma for post-therapy imaging to ensure that the microspheres or the treatment has reached the correct or targeted location. The methodology of forming my formulation is using water and oil water solvent evaporation method, where we dissolved samarium, PHPV, and doxorubicin in chloroform. After that, the microspheres has formed, collected, dried in the oven, and then sent for nutrient activation. Now, nutrient activation occurred at the reactor at the Malaysian Nuclear Agency, where the Sm-153 was activated. So the nutrient activation with irradiation of 5 hours to convert the non-radioactive samarium into a radioactive samarium, Sm-153. After irradiation and cooling, gamma spectroscopy was conducted to ensure that there's no radionuclide impurities. So in the results, radioactivity of the DOX-SM-PHV microspheres had a specific activity of 8.68 gigabecquerel per gram, where the activity per microsphere was 177.69 becquerel per microsphere, compared to the commercially present deuterium-90 resin and glass, which had the activity per microsphere from 50 to 2,500 becquerel per microsphere. Therefore, this is an appropriate range for the current treatments. As well as compared with other papers which use samarium particles or microsphere, activity per microsphere of Doxorubicin and PHPV was higher compared to other papers. Now, a HPLC analysis was conducted for DOX before and after neutron activation to ensure that the neutron activation does not affect the DOX. And we had a similar retention time before and after. Now, using SCM, Doxorubicin PHPV microsphere before and after neutron activation, it kept its shape, which was spherical and no fragmentation. And the mean diameter was 13 micron with a size distribution from 25 to 37 microns, which is a suitable size for transarterial radioembolization to ensure that the microspheres are not too small, that they will go to other organs such as the lungs, yet not too big that it will actually block the blood flow at an earlier stages far from the tumor. Now, the EDX also showed that there was no elemental contamination. So we had the samarium from the samarium, oxygen and carbon from the PHPV, and platinum from the coating for imaging purposes. Now, based on the thermal stability, the microspheres had to be able to withstand the temperature of the reactor, which will not top up more than 40 degrees Celsius. The thermal stability of the microsphere of Doxorubicin was 155 degrees Celsius. Based on the FTR to ensure that the samarium and the doxorubicin were integrated into the PHPV, as well as the Doxorubicin PHPV before and after neutron activation does not have any elemental changes. So the peaks of the PHPV, the samarium, and the doxorubicin can be seen in the Doxorubicin PHPV microsphere. Therefore, they successfully integrated. And the peaks for Doxorubicin PHPV before and after neutron activation was similar. Therefore, there was no elemental changes. Now, the radionuclide retention efficiency is a test to ensure that the radionuclide does not seep out of the microsphere, therefore will not go throughout the blood system and affect other organs. So it's tested in pH 7.4, pH 5.5, and blood plasma. So you can see the retention efficiency was very good, where it was more than 99%. This ensured within 600 hours, which shows that the retention efficiency is quite high. Comparison with other samarium and other radionuclides, which usually is above to 95 or 98. Now, in vitro DOX release was conducted at PBS at pH 7.4 and pH 5.5. So at 7.4, 65.21% of DOX was released, and 29.96 at pH 5.5 up to 1,000 hours. This is to ensure that this is a desirable property of slow, steady release of the doxorubicin, so that even after the decay of the radionuclide, there's still treatment being released towards the tumor. So that even after the tumor cells that are trying to recover from the radiation, there's a doxorubicin which ensures that the tumor cells could actually die. And now, the in vitro cytotoxicity test was conducted using MTT assay on HepG2 cell line, which is a liver cancer cell line. For comparison purposes, we used radioactive microspheres alone, the combined therapy of DOX and samarium, which is chemotherapy and radiation together, and chemotherapy alone DOX PHPV microspheres. So as the concentration increases, the cell viability decreases, and it's apparent that you can see the lowest cell viability was for the combined DOX and PHPV microsphere, and at 300 microgram and between 250 and 300 microgram of microsphere per ml. This shows that the combined therapy had more effect on the cell viability of HepG2 cell lines in comparison of chemo alone and radiation alone. The content of doxorubicin in the microspheres was 0.036 milligram per gram, and the samarium content was 12.8%. Current applications for the combined therapy, as you can see, other clinical trials have tried to conducted using systematic chemotherapy in deuterium microsphere, as well as TARE, transarterial radioembolization with sorafenib, and showed that the combined therapy had better results and compared to single. Now, for the potential applications of Dox-SM PHPV microspheres is where we have the gamma, beta, and doxorubicin, where the doxorubicin and the beta will be for the treatment of the tumors, and the gamma is for post-therapy imaging to ensure that the microspheres reach the correct location, as well as it's more focused and concentrated of the radiation in one location. So in conclusion, a biodegradable chemo-radioembolic microsphere Dox and Sm-153 was successfully developed for synergetic chemo-radioembolization effect on liver cancer HepG2.